for SSGC, which is Sri Southern Gas Company. That's the largest gas supplier in the south region of Pakistan. So currently what SSGC is doing is that they are manually reading the gas meters. So our task is to automate this project. So before going towards the details of our project, let's first explore why the current solutions are not optimal for our problem. So here on the left hand side of the screen, you can see a very crystal clear image of the meter, which is quite easily accessible and which is quite easily readable by the human eye. When we run it through the Tesseract OCR, we can see that the results are 100% accurate. But after that, on the right hand side of the screen, you can see a little blurry image which is not taken in a very controlled environment. When we ran that image through the Tesseract OCR, unsurprisingly, we did not get correct results. Like you can see at the image on the right hand side. So we've got like 1.5 million images like that which are not taken in a controlled environment. Which is why when we ran it through different types of OCRs, you can see the results here in the graphs below. Like the highest accuracy that we got was on Google Lens, which was 70%, which is nothing compared to when we tried the Google Lens API on our project, that was just 20%. That is because these OCRs have been trained on images on a very controlled environment. Whereas the images on the right hand side, we've got like 30% of our data set on an uncontrolled environment, like the images on that. So that's why these models could not perform well. Well, the first challenge that I highlighted on the previous slide was inaccuracy. Apart from that, the challenges that we are currently facing on the manual meter reading is firstly human dependency. That we are quite dependent on the meter readers, that they should be expert on the work they do. Apart from that, they should concentrate well on their tasks. Secondly, unreachable meters. Some meters are quite distant from the meter reader and they are not readable by the human eye. And thirdly, limited information. Like in the manual meter reading, there's just a limited information, just the meter number that the meter reader provides us. Well,
now basically in order to come up with the right approach, we started off with implementing some first fundamental steps. These fundamental steps are divided into two sub-steps. Number one includes the use of morphological image pre-processing techniques and image reconstruction techniques, followed by some open popular source OCRs such as Keras OCRs, Tesseract, Google Lens, and Vision APIs. Like my friend mentioned, the highest accuracy we got from it was 20%, not more than that. Then we tried some conventional machine learning models such as ResNet, LeanNet, AvisionNet. And even with implementing the transfer learning, we had a cap of accuracy of no more than 60% on that. So after that, after this part, we had to change our technique, and we started off with some state-of-the-art computer vision recent models. These includes vision transformers, zero shot learnings, and some really highly grounding techniques like grounding. Even though these performance were better and competitive to the conventional one, these have very high computational resources, they require very high computational resources, and they have a very complex architecture that makes it infeasible to use in the real-time scenario. Now that is why now let's come to our approach that we use. After the intensive approach, we had to come up with a solution that lies in between the contemporary machine learning, that is the classical machine learning, and the state of the art. So we had to lie in between somewhere. After intensive research, we had finalized and we divided our problem into object detection plus object segmentation problem. We started off with a parent image and we passed that image into an object detection model. That outputs us the region of interest, which is the black box in our scenario, which is what we want. This output is followed to the object segmentation model, which subdivides the images into the 5 different images. Now, these are the digits that we want. We finally pass those images into a specialized convolution neural networks that is specialized, and it has some layers which are very different. Now, before we go ahead, let's take a look at the demo and see how it works in our use case. Now, this is login state. We have made sure this application is, by the way, developed on Flutter. We have made sure that whoever is a meter reader, they have to sign up, they have to log in first before they go ahead. So this is an additional security measure. log in. And here we go. Every time the meter reader receives, they have a list of Excel files that they receive from their operator, and that has certain information that includes the meter number, address, and the meter reading. Now what their job is, they have an option to enter the meter reading manually if they are not satisfied with the reading they are getting. So first option is to write the meter readings number manually. This is because no system is 100% accurate, and we believe there is always an room for improvement. Now the second option is what we are here for. We have an option like Google Lens. They provide us a box. You take a picture of the box, and that's all. Then you rely on our system. Then you press OK, and this picture will be saved as a copy in our database in the Firebase. We make sure this is for the legal purposes because it's required by the government. And if the meter digit is right, you will go ahead and press submit. If the reading is not correct, you have an option to recorrect it, but this is very important because we have to learn from our mistakes. So we focus on active learning. What we do is we simply take a copy of this picture and the right reading and store it in our database. And every 2 weeks, we include these wrongly classified images into our training pipeline, and we retrain our data so that now our model sees these inaccurate examples. So we try to improve every 2 weeks. We try to come up with a better model than the existing one. Now let's go ahead. This is basically simply the comprehensive comparison. We took a sample of the testing data set and ran it through different models, EfficientNet, Google Lens, everything that you can see there are just 12 out of many models, and we have the highest accuracy of 96.02%, which is with our model.
Alright, so moving towards how we covered up the challenges. Firstly, as we saw in the previous slide, currently our product gives an accuracy of 96%, which solves our first challenge of inaccuracy. Second challenge that we had was the human dependency. Before moving towards how we solve the second challenge, let's first look at the meter image again. Apart from the meter reading that we are interested in, we also have a meter number. This meter number we have used for validation check. How we are doing the validation? We are first extracting this meter number through an OCR, and when the meter reader goes to read any meter, he first has to verify the meter number. He first has to verify that he is reading the meter correctly and he is reading the meter in a correct sequence, because he is given a correct sequence that he has to read the meters in. So the sequence is matched, the meter number is matched, and then the meter reading is matched. That's how we have covered up the human dependency error. Like a person cannot read a wrong meter, or a person cannot go out of the sequence. The third one is unreachable meters. The third challenge that we had was unreachable meters. But right now we've covered this through an easy approach that the meter reader no longer has to read the meter through his naked eye. He just has to make sure that he can click the picture of the meter and his task is done. The output will be shown to him, and no meter is unreachable anymore. The last challenge, that is the most important one, is that earlier we had limited information. Through manual reading, the meter reader could only input the meter reading. Only this thing was inputted. But now what we are taking is that on every customer we are storing the data for the past 6 months, which means that we have calculated a threshold, and let's say if a meter reading goes above the threshold or below the threshold, that outlines an anomaly. That this meter reading is an abnormal meter reading that exceeds, or it is very low than the average meter reading for the past 6 months. So that outlines an anomaly, and that shows the meter reader that something is wrong with the meter reading. So that is reported to the higher authorities, and preventive measures are taken accordingly. This actually prevents high financial losses as well as gas theft. Alright, so are we compatible and are we interoperable in the industry? Yes. Why? Because we have used Microsoft AWS for the deployment of the project. Secondly, we've used RoboFlow for the image annotation, which is a quite powerful tool in today's world for computer vision. We've used Flutter for the front-end development. We've used Git for vision control, as well as we've used GeForce RTX GPU, which is a very common and very simple GPU. It can easily be accessible. So if someone wants to replicate our solution, or if someone wants to reuse our solution, they can easily do that because this GPU is easily accessible. And lastly, we've used raw images, which is very important for the processing of images.
Okay, and last but not the least, we make sure that our system is based on software entirely. Current is based on hardware plus software, so we make sure we are compatible and adaptable to any smartphone that they currently use. All they have to do is just log in, have some biometric checks and security checks, and you're good to go with the media reading process. So that's it from our side. If you have any questions, we will be more than happy to answer them. Thank you.